Boa tarde.
Okay, so this will be a short talk from Lucas Fonseca, right? Also from University of São Carlos. I'm right?
Yes.
Okay, I'm right. Federal University of São Carlos. So, well, please go on. Floor is yours.
So actually, I'm going to present the work that I developed during my master's, and then back then I was in UFMG, but I recently joined Yara's Kobato group as a PhD student, and there will be a lot of similarities, and that's why we are here to discuss this coupling with the 2D magnets. But I will not enter too much of that. So I will talk about the observation of dark doublets in single photon emitters in TMDs, as it's a quite interesting emission we observed. So this talk is divided in a few subsections where I will present the optical properties of TMDs, similar to Yara, but I will go a little bit slower. I will also explain why the magneto-PL is so important for us. It's our main optical characterization. Yes. But I will also talk about nano-PL. I came from a group that is specialized in sample preparation, so I will also talk a little bit about that and to the materials, present the results and why we are here, and moving forward what we want to do. So I think everyone knows, but TNDs is the combination of a transition metal plus a chalcogenide, and you can combine in a lot of different combinations depending on what properties do you want to access. So similar to graphene, it presents a hexagonal crystal structure, and its form of stacking van der Waals layers. And as Yara mentioned, when you reduce the dimensionality of the system, you have a reduction on the interlayer coupling of the material, and it affects this gamma point heavily, which then changes the band gap from a indirect to a direct band gap, and then we have a strong emission on the monolayer. So for example, if we use a mercury light source, we can see that the monolayer regions, which are barely seen in this optical picture, emits a lot of light, while few layers do not, and exemplifying the transition from indirect to direct band gap. So that's why we're studying monolayers. And also, when we reduce the dimensionality of our system, we have two major effects playing. We have a weakened electrostatic screening, so the electrons can see each other much more easily because there are less atoms on the crystal. Plus, you have a 2D confinement, which also helps to generate this excitonic behavior. So the optics are dominated by excitons, trions, biexcitons, charged biexcitons, and so on. You can combine 5 quasi-particles, and it gets a little bit crazy. But in TMDs, there are for describing excitons, there are two main characteristics. There are the bound energy. In TMDs, it can vary from 0.3 to 0.8 electron volts, and we have a Bohr radius of 1 nanometer. So it's a little bit bigger than the unit cell. It's several unit cells. And also we have these two important properties where we have, for monolayers and odd layers, a break of inversion symmetry. So for example, if we put our inversion center in the green atom of the transition metal, we can see that this atom should be on the other side of the crystal structure to protect the inversion symmetry, which do not happen. However, for even layers, we do have inversion symmetry between the two layers. Plus, we have a strong spin-orbit coupling that arises from the d orbitals of the transition metal, which are known to be related to a high angular momentum. So the spin of the electron is coupled to its orbital angular momentum, and we have energy bands that are preselected in spin. So for example, in red, we have the allowed energies for the electron with spin up, and in blue, we have the allowed energy for the electron spin down, and the valley where the direct band gap is located is linked to time reversal symmetry. So the spins are opposite, and then if we zoom into these points, we have a variety of possibilities for the optical transitions that I will go one of them individually. So for the first one, we have the bright exciton, which are related to energy bands, which has the same spin. So this emission it normally dominates the spectrum, as it concerns both spin and momentum. So the bright exciton has a dipole in the in plane of the monolayer, and so can couple efficiently with laser, which is normally shine on the perpendicular. And we also collect the light in perpendicular, so this is the bright exciton because it's dominant on the spectrum. But we also have what we call the dark excitons, which for WSe2, that's the material of the work, is really important. As if you see, the lowest energy transition is dark. So the ground state of the material is dark. We will have quasi-particles that have a higher lifetime and cannot emit radiatively. But we also have to consider that this effect happens in the two valleys. So whenever we have this degeneracy of the valleys, we have a coherent superposition of states from both valleys. So we need to, when we have this condition, we have to consider two possibilities. We can combine these spin configurations in a symmetric and an anti-symmetric form, which causes us to call this the gray exciton, and this is the totally dark exciton, which have difference in their emission lights. And this one actually can emit on the in plane, but normally what we do is PL perpendicular to the sample, so this is not observed normally as well. And we also have the dark exciton where the spin matches, but we do not, it's not located in the same momentum. And we also have the bound excitons that are transitions related to middle gap states due to impurities and defects within the material, and this will actually play a major role in our formation of the single photon. Another thing that I just want to present is that the valence band of this material are formed by this combination of orbitals. So we have the plus and the minus, and so the valence band on the two valleys are actually not equivalent when we consider their irreducible representations. So when we consider the representation of the exciton on the conduction band and the hole in the valence band, we actually encounter two different symmetries for the K and the K prime valley, which couples with light with opposite polarizations. So for example, if we probe our sample with right-handed circular polarization, we only see this K valley, while if we change by left-handed circular polarization, we only collect from the K prime valley. However, this is not perfect within the material because we have exchange interactions coupling the two valleys. Yes.
I have a quick question regarding the selection rules from the previous slides. So usually when we calculate, so usually when we calculate this, we use the reduced representation of the conduction valence band of both, but also of the interacting Hamiltonian connecting conduction and valence band. So in this case it would be A dot P, right, the dipole. So why this does not enter into your analysis?
I do not remember if they actually addressed this Hamiltonian, because they were only considering the symmetries of the electron, the hole. So this is the complex conjugate, but in the article. But I don't think this is addressed on the article. Yeah, also sorry, I don't remember where the Hamiltonian. I don't know if it's different on the two conditions, and that's why they maybe didn't consider. I'm actually not a specialist in theory group. So as I'm mentioning, this is not perfect because we have exchange interactions. But for example, when we use a resonant laser, we can see that when we shine light with sigma plus, so we are in this valley, and you can collect on the same valley, we have strong bright exciton emission. But when we use the cross polarization, we can see that the bright exciton reduces in intention, but it should be 0. But we have to consider the exchange interactions. So the exciton, so we need to imagine the exciton as an immerse in a sea of other indistinguishable particles. So its wave function will also encounter other electrons, other holes, and other excitons. And this can be actually get pretty difficult to address theoretically too, because you have to consider a lot of things. And it's also divided in long range, short range, and it also depends on the angle, on the center of mass of the exciton. So for example, when we perform resonant photoluminescence, the center of mass of the exciton is near 0, and we have less exchange interactions happening. But when we move to other conditions, this can get really difficult, and it can couple the K and the K prime valley, lowering this valley polarization, and this also causes energy difference between the gray and the dark exciton related to these exchange interactions. So in 2015, a group saw that on random positions, there were emissions with very low, narrow line widths and really strong intensities. And this occurs randomly on the sample and more often near the borders. So they started to experimentally probe what these emissions were, and they found out that it were related to single photon emitters, as they presented an anti-bunking effect. So it's actually emitting one photon at a time, but it occurred randomly. But moving on, they perform a lot of experiments where they could nanoposition these nanopillars by introducing strain on the sample. So, for example, in this work, they will use the nanopillars, and within the regions of the nanopillars, we have the appearance of these very narrow peaks. And it also appears in bubbles when you perform nano-indentation, where you take the tip and pressure your TMD, and many other strain applications. So we need to understand what the strain is doing to the energy bands of the material. So, for example, the strain that the nanopillars are inducing is a tensile strain, which reduces the angle between the two selenium atoms and thus reduces the coupling between the orbitals of the chalcogen, which is P, and the WSe2 orbitals of the transition metal. When you perform DFT, this group here showed that this results in a reduction of the energy gap of the TMD within these strain locations. And then we have two effects. First, we have this lowering of the conduction band, and we have what we call the exciton funneling, because the exciton tends to funnel to these minimum energy locations and get confinement within this potential, which increases the quantum yield. So the regions of the nanopillar emits a lot of light, normally. But if we reduce the conduction band enough, we can actually cause it to approximate with a defect level, causing a hybridization between this defect and the conduction band. But if you remember, the conduction band, the minimum energy was related to a dark band, which the spin could not recombine radiatively. So what this hybridization actually do is actually promotes the brightening of an otherwise dark transition. Now this emission can actually emit light. And similar to the dark exciton, it can also be in a symmetric and an antisymmetric form, which the exchange interaction breaks this degeneracy, and the single photon always appear as these two-way emissions, which presented a linear polarization with 90 degrees. And this will be important, as this will be the main difference of the dark doublets. So this cannot account for our result, as we are seeing 4 emission lines within our doublet. So we need to implement a little bit more. So talking about the magneto-PL, this is a PL for a strained WSe2, and we can see that there are a lot of peaks. I don't know how I couldn't tell you which is quasi-particle. So we need something to resolve these energy peaks, and we do that by applying magnetic field. So what we do is we access the information about the orbital and the spin of a given transition, because we analyze the Zeeman shift of each given peak. So we have the energy shift, what we call the G factor. There is the proportionality between the magnetic field and the energy shift. And we can then understand which transition is the bright exciton, the tri, and so on. For example, for the bright exciton, the energy field will break the degeneracy and the time reverse symmetry, and we will have a lower energy gap and a higher energy gap, and we have two different emissions for the bright exciton. One with right-handed circular polarization and the one sigma minus. For the dark exciton, we actually have this parabolical dependence due to the exchange interactions, but it's similar to the bright exciton, but with a higher G factor of 9. We can actually get 8 to 14 for momentum dark, and we can also use a parallel. I forgot to say this was perpendicular because of its Zeeman shift, and we can also apply a in-plane magnetic field. And what this causes, it actually induces a spin flip, spin precession of the spins of the transition, and you can actually mix dark and bright transitions. So the dark exciton starts to appear when we apply the magnetic field due to this component of the magnetic field. So moving to the sample preparation. So we prepare a nanopillar sample where we develop a way of creating these nanopillars by electron beam lithography. The main, so we did start a bit deformed, but then we got the circular shapes and very narrow line widths. And the main important thing here is because we developed this method of electron beam lithography on polymer, we induce crosslinks and the nanopillar are transparent. This is the major difference between the other nanopillars, and this will be very important when we perform nano-PL. So this is the basis of the 2D preparation. We exfoliated the TMD, we optically characterized it, found the monolayers, we confirmed with Raman and PL measurements, and we moved to our transfer machine, where we adhere a polycarbonate to this PDM's pyramids. So here's the sample on a heater. So we touch our substrate, we increases the temperature, so the polycarbonate expands, and then we reduces again, and the flakes are picked up by this technique, so we can create heterostructures and control the twist angle and so on. We also, this work is in collaboration with Márcio Daldin group, where we uses his auto cube, where we can apply perpendicular and parallel magnetic fields up to 9 Tesla, and we can change the optical excitation and couple the detection channel with fiber or free space optics that will change our resolution of our spectrum. So moving to results, this is our sample. So as I'm saying, then this region of nanopillars have a higher quantum yield, so it emits a lot of light. And it's shifted due to strain. So this is a spectrum of these nanopillar regions where we use this free space optics, which we collect an area from a large sample, much beyond the limits of the laser. So we get this spectrum with a lot of narrow peaks. When we change to fiber couple modes, the fiber acts as a pinhole, and then we get a confocal system where we can clean this spectrum by a lot, and we can actually observe single photon spectra, so we can address them individually, mostly. For example, these three appears together, and we can see their fine structure splitting, and so on. So when we apply the magnetic field, they all experience Zeeman shift and get heavily polarized within the valley which has the lower energy gap. For example, for the K prime valley, the lower energy gap occurs in the values of -B. So the single photon get heavily polarized in this valley, while the opposite thing happens for the other valley for positive magnetic field. So we will focus on this doublet, which is the highest intensity, and we actually see a quite interesting behavior because we can actually see 4 emission lines. We have this and this, which has a lot of energy, a lot of intensity, and we have these two faint ones that appears within our spectra, which is not expected. For example, in a high magnetic field, 9 Tesla, we actually can still see a fine structure splitting normally seen in zero magnetic field. So these two peaks are shifting together, and we need to understand the difference between these two peaks. And they actually have the same G factor and similar fine structure splitting, although this one has a little bit of more, but we cannot actually obtain these values because this doublet is actually related to what we call the dark doublet, which is associated with spin flip process. So another difference is in the dependent intensity modulated by the magnetic field. We can see that this bright doublet gets heavily enhanced by the magnetic field, while the dark doublet have a very lower enhance in the intensity, but they do present the same valley polarization. So this is not due to thermal shifts. This is actually difference because of the nature of these doublets. So what is happening in zero magnetic field? We have a coherent superposition of states from both valleys, which gives a linear polarization. When we break the valleys degeneracy, these doublets get collapsed in one valley and acquire its circular polarization depending on the valley in which they get selected. For example, sigma plus and sigma minus. And the opposite thing happens for the other magnetic field. But what we do have is another doublet here, which are related to an intra-valley spin flip. So is this emission within the same valley? And we have a very complex scenario. We have a fine structure splitting between the bright transitions. We have an exchange interaction between the dark transitions, but we also have an exchange interaction between the bright and dark transitions within the same valley, because the two doublets are shifted in energy and are not degenerate. Another important difference, this is the linear polarization of a standard doublet. So we vary the linear polarization of the detection light, and this is the standard behavior where we get this 90 angle offset. But in this our bright dark mix, the states, the polarization is very different. For example, the lowest in energy and the highest in energy are actually shifted with 45 offset degree, and the middle state do not present linear polarization, as it's a degeneracy between the two states of the doublet, asymmetric and antisymmetric. We actually suggest, but we cannot test experimentally, that this might be due to a different combination of each basis. For example, for the bright doublet, we have the axis related to this catch and this other catch. When we consider the combinations, we get the linear polarization in 90 degrees. Well, what we suggest, but we cannot test or anything like that, is just to think, is that if we add a complex coefficient to these catches, which are dark, we can actually generate a 45 offset angle. But this is just a suggestion, and we cannot actually move forward. And we do not know what this would physically mean in our system. And another thing that happens is when we put an in-plane magnetic field, we actually are observing a high Zeeman shift, which cannot be accounted for a fully in-plane magnetic field. So there are problems occurring. These dark doublets were not supposed to be seen in perpendicular magnetic field, and these were not supposed to be seen in the in-plane magnetic field. And what is happening is actually we're seeing a doublet that are located in the curved region of the nanopillar. So the components of the magnetic field are actually mixed. So we are not applying a fully Z magnetic field, but rather a mixture of the two components. So that's why we are observing different behaviors, and we are able to characterize this dark doublet. So probing the location of the single photon can be really important. And that's why we use transparent nanopillars, so we can actually perform what we call the nano-PL, where we use a tip enhancement photoluminescence to increase our resolution. So now the resolution is not given by the laser spot, but rather this tip diameter of within 20 nanometers. So, but our experimental setup is limited to backlight illumination. That's why this nanopillar needs to be transparent. So our idea is, this is the single photon. When we increase the temperature, the potential confinement of the defect gets broken and the single photon dies. But if we increase our resolution, we don't need a higher confinement, so we can actually observe emissions. And this is a real photo of our sample, so we can see this tip approaching our sample. It needs to be really close for it to work. And this is the illustration that I designed, but the other group has very more beautiful photos that are professional, but I think this is more charming. And so I will just really go quickly because I cannot enter this project. But what we observed is within the nanopillar borders, there was an emergence of a localized peak, which is very distant from the shifted bright exciton. So it's actually, I didn't put here, but it's up to hundreds of millielectron volts. Is like 120, so it's probably a defect. It cannot be a trion, it cannot be a fully dark exciton. So we believe this is associated with a defect. And it only occurs within the nanopillar of borders of this nanopillar, while wrinkles, which actually have higher strain than the nanopillar, do not present this localized emission. So actually the relation with strain is not linear. Okay, there was supposed to be another photo where we see the top of the nanopillar, and this localized emission is not homogeneous within the top of the nanopillar. They are actually confined in small regions where its maximum happens within our resolution of 20 nanometers. I forgot to mention, but these maps, these PL maps, are very, very small. It's 300 nanometers wide. And we observe the same things on platforms, on the interfaces, and this is another in wrinkles of the platform where we can see this localized emission in these interfaces. So it's really related to strain. Although bigger pillars, this one is near 1 micron, do not present the localized emission, only in this specific border, which happens in the same energy of the other emission. So the question is, why are we here? And probably everyone already considering, we are talking about CSB, CRSBR, as Yara mentioned, because this material has a magneto-exciton coupling. So where this antiferromagnetic phase can actually interact with the magnets, which can induce a transition hybridization within the antiferromagnetic. So the energy of the bright exciton of the exciton of the CSB actually has a transition. It changes in time, and this frequency is within the energy of the magnum. That's why they can probe the magnum. And we wonder what this could imply to our single photon emitter. As the Yara already mentioned, its exciton can be used as a probe of the magnetic phase. I will not talk about that. So what Zé Roberto is studying now is a localized emission within the CSB. And then we observe a lot of different effects. It can change the linear polarization, but this is just hypothesis on what we can achieve with this coupling, because the sample was a single photon spontaneous. We do not produce the single photon as are produced in the nanopillars. But we believe that we can also alter G factors. We can maybe enable these dark doublets with the magnetic moment. So we have a lot of possibilities for magnetic heterostructures. We can use the strain to change these interlayer exchange interactions. We can twist angle and so on. So we have a lot of possibilities, a lot of ideas, and not much time. But Yeah, so the conclusion is that TMDs are great toy models for studying fundamental physics, and CSB and other magnetic materials can offer avenues for single photon manipulation. And this is just open. And everyone that helped me during my master's, and I'll also thank my new advisor for this. Yeah. No. Yeah, that's all.
Thank you. So questions, remarks. So I think I can start. Very nice talk. Well, you already answered. To be honest, I was with a question about how is this minimal size of the nanopillar to see these features. But I think you mentioned already, right?
Yeah, you mean the diameter?
Yeah.
Yeah, it's actually a crucial aspect. It's not only strain, you need to confine locally. We cannot, otherwise you don't have this strong confinement. So we need to be really localized. Yeah, that's it. I forgot to mention that maybe if we could, in further future, couple this nanotechnique, nano-PL, with magnetic fields. So we could actually have a way of nanosensing magnons and magnetic phases using PL, but we are very far from that because this is very difficult experimentally. But if we could, it would be awesome.
I have heard that this technique to with the tip that you go right on top is very
yeah, the enhancement can get
I heard about it.
can be 30 times the intensity.
Just Ingrid.
Thank you, Lucas. Nice talk. It's just a curiosity because I show in your experiment use the tip. It's a metallic tip. And could you see some plasmonic effect in your measurement? Because when you excite the gold tip with the laser, probably we are probing plasmon as well.
Yeah, probably we are also probing that, but we didn't try to see this. I don't even know what's the energy range or what I was supposed to see. But yeah, maybe it's a possibility. And one important thing that I didn't mention is that this tip, it's acting like a near field. So its enhancement of the electric field is due to this plasmonic effect, and the electric field actually gets similar to a dipole. So the electric field is like that. So we are probably seeing dark states because of this different configuration of the electric field. You can maybe picturize as a dipole on a plane.
Maybe, yeah.
Very stupid question. So I'm by far not an expert on excitons. You have talked about like dark excitons, and as far as I remember, the dark excitons, they do not couple to light, so
Yes.
you cannot see them. So how do you see them here?
So this is the role of the curvature of our nanopillar. So when we have the components of the magnetic field, the spin actually have the components. So for example, this is the bright and this is the dark. When there do this effect of the curvature, we have projections within this X and Y plane of the TMD, and you actually get the states mixed. So it's like you put...
Okay, so you're hybridizing dark and bright.
turns in the Hamiltonian diagonally, and then the states get mixed.
Sounds good. Thank you.
This is only seen on a few positions. It's not all nanopillar that presents this.
More questions? So maybe I can have the last one very quickly. You mentioned that, well, if I understood, you made the nanopillar because you was thinking ahead that you're going to do the nano-PL.
Yeah,
right?
our main idea was to investigate
Yeah.
using the
So
nano-PL.
that's why you use this nano-pillar as transparent.
Yes,
Yeah.
it's there.
But this is the only, let's say, restriction to
of,
be transparent?
of our TPL.
Nano-pillar, for the nano-pillar. The only constraint is to be transparent?
No, there's
material,
actually
or-
not another because the substrate also needs to be transparent.
Sure.
So we cannot use SeO2. So
Yeah, but I mean,
the sample needs to be in a quartz plate, and this is a very important restriction because not every sample can be.
Okay.
You need to transfer from silicon to this quartz
yeah.
plate, and not every. And even the nanopillars we produce on this quartz was different because this nanopillar is produced by cross-linking the polymer. So if the charge transfer of the substrate is not good, as in the quartz,
Yeah.
it can actually get more bigger than you wanted. That's why I got this big pillar distortion. I did not intentionally produce him.
Nice. So if you don't have questions, shall we take again the speaker?
All right, thank you, Roberto, for